Welcome to the place where we gain knowledge through the lens of creativity. I am Aaron Dworkin, and this is Artful Science. Thanks again for joining me here on Artful Science. Today's show is Biosignatures, Breath of Life. And my guest is Max Coleman, who serves as a senior research scientist at the NASA Jet Propulsion Laboratory at Caltech. Max, welcome to the show.
Aaron, thank you very much. It's a pleasure and a privilege to talk with you today.
Oh, well, thank you so much. And I am really excited to learn about biosignatures, something that definitely, especially as a lifelong artist, I do not have a lot of knowledge about. So I thought I'd just kind of start out. You spend, much of your life kind of really looking for other life. And so when we think about looking for other life, I think of just kind of normal or being a Star Trek fan and we look out to other planets or, something like that. But when you think about looking for other life, how do you do that? And what exactly are biosignatures?
Okay, well, I focus on other life in the solar system, which we could expect to be a bit Earth-like. Not completely, but a bit Earth-like. And what am I looking for? I'm looking for something which says there was a living organism. Now, Earth is our best model, the only life that we know. For a lot of its history, it started 4.5 billion years ago. Maybe as soon as 4 billion years ago, life started. And it didn't come into large forms of life that leave normal fossils until maybe 500 million, just a bit more than 500 million years ago. So for most of its history, life on Earth was microbes. And that's what I'm looking for, microbes. Now, biosignature is anything which is a sign of life, either actual or in the past.
Great, awesome. And so when we think about that, and it's interesting, so microbes have been around just so much longer than what we might more commonly think of as life. Just to help our audience and for me to understand, when you describe microbes, is that it can't be seen by the naked eye? How kind of small are we talking? What are we thinking?
Oh, we're talking about a millionth of a meter, a micron. I don't know what that is in imperial, but it's very small. You can't see it. It's about the limit of what you can see with a microscope, a normal microscope. And it will be things like bacteria and viruses also, but I'm more concerned with bacteria.
Gotcha. Awesome. Awesome. So when we think about bacteria and looking for them, so there's this, I guess, idea of their breath, and that somehow that creates something, or we can learn from that. How does that work, and what is kind of involved with that breath of bacteria?
Yeah, well, all organisms have metabolisms, and they breathe in stuff and they breathe out stuff, and they process stuff that they eat to make energy. And bacteria do the same. They eat, for example, organic matter, and they breathe out, as we do, carbon dioxide. So, burning carbs is what you do to get energy, and those carbs can be carbohydrates or other organic matter. And instead of burning them at high temperature, you have metabolic processes. In our case, as humans, mammals, using oxygen from the atmosphere to burn carbs to give us energy, and we breathe out carbon dioxide, carbon from the carbohydrate, oxidized to carbon dioxide, and all organisms breathe out stuff.
Wow. And so this is, as I think about that, and I think about my own breath and breathing out, is that carbon dioxide the same as bacteria? Obviously much, much, much smaller. But is it literally the same?
It's the same process. And the carbon dioxide that you breathe out is distinctive in that the carbon that it started off from is organic carbon, which is isotopically distinct. I don't want to go into detail, but we can characterize breath, and it is proven easily that it's the result of what we eat and what we burn.
Wow.
And that's the same for many, many, many sorts of organisms. They have metabolisms, that they breathe in oxygen, they breathe out carbon dioxide. But bacteria are very versatile little beasts. In the oceans, there are bacteria which do the same as we do. They breathe in oxygen, which is dissolved in the water, and they breathe out carbon dioxide. There are other organisms which, if there's not enough oxygen around, use a compound dissolved in ocean water, sulfate, and they use the oxygen in the sulfate to burn the carbs. And there are other organisms which use rust, iron oxide, occurring naturally, which again is used to make their metabolisms work, and they breathe out carbon dioxide. So a combination of the carbon dioxide they breathe out and the other compounds and chemical stuff that they produce as a result of their metabolisms tell us what sort of bacteria there were that were operating in the past or even at the present.
Fascinating. And so the nature of whatever they breathe out can help us to identify what they are. So how do we look for that? So if you're looking for, bacteria or this evidence, and it may be, from, millions of years ago or whatever, how do you see it? How do you track? How do you find it?
It gets turned into stone. I mean, this is the miracle of chemistry and geology. Now, you look a little bit incredulous at this, and I don't blame you. How do you get breath turned into stone? Well, now let me just go back a bit. For many years, I was associated with the Royal Institution in London, Great Britain. And that's got over 200 years of history of eminent scientists working there and being invited in there. And the thing that they do regularly, at least once a week, is have a public lecture. And in the olden days, the public lectures were the most eminent, as they still are, the most eminent scientists of the day, who would stand in front of the evening audience there, all with their tuxes on or white tie, and they would not only talk, they would show. So this is a tell and show place. And they would do experiments or displays. And my idea when you invited me to talk to you was, hey, I'm going to subvert his format. I am going to do an experiment in front of him.
All right.
And I thought again, yeah, experiments are dangerous. The danger being they might go wrong and you look pretty stupid. Nevertheless, in my public talks, I do actually do at least one or two experiments. So what I'm going to ask you to do now is to imagine the experiment I'm going to describe to you about turning breath into stone.
Okay.
So I have in front of me a test tube. You can imagine that. It's full of a colorless liquid, which I've just poured into it. And that colorless liquid is a solution of limestone, effectively, of lime. It's lime water. It's calcium hydroxide. It's lye, and it's colorless. And then I have a narrow, thin tube, which I poke into it. I put the other end into my mouth, and I breathe out, bubbling it, breathing in through my nose and out through my mouth. So there's a constant stream of bubbles. And amazingly, in less than a minute, that turns cloudy. That cloudiness is, in fact, calcium carbonate, limestone, produced from the carbon dioxide of my breath. And then, when I've done that, and it's clearly cloudy, but it's not a lot of it, I challenge the audience. Now, that's going to be you, because you're the only audience available at the moment. I say, hey, guess how much limestone I would produce in 1 year. So, don't calculate it. Aaron, guess. Give me a number, a weight of limestone. A mass.
6 ounces.
6 ounces. That's a great guess. I'm afraid you're going to have to go higher, but I'm not going to prolong this at the moment. In fact, it's quite easy to calculate and prove. In a year, I would produce 1,600 pounds 1,700 pounds, getting on for a ton of limestone just from what I breathe out. That is a pretty noticeable biosignature.
Of course.
And the great thing about biosignatures like that is that they can lead us to the organism which has been breathing out, and then the more fragile biosignatures like lipids, the cell walls of bacteria, can actually be found in a very small. Let me show you a biosignature. I put it next to my head for scale. This is a 4.5 pound biosignature produced in the early Jurassic, 190 million years ago, by bacteria living in the oceans, in mud, and they were breathing out for a relatively short period of time, and they produced, as part of an ecosystem, they worked with the sulfate oxygen, they worked together with their buddies who were the rust eaters or breathers, and produced this.
Wow.
And that's great, because if you're a geologist, you go out and you look at an outcrop, these stand out.
Right.
And you can go into them and say, wow.
Right.
That has got not only all this stuff which we can recognize, but also the much more frail biosignatures, the organic matter.
It's truly phenomenal. And so literally then through that, you're able to identify what bacteria were living there and when they lived there.
Well, when is a different problem. We know the age of the rocks, but I've worked on rocks as young as 50 years old, which have been turned, they're mud, they're salt marshes, where the mud has been turned into rock, and things which are more than twice as old as that. So we can look at them and say, yeah, we understand that microbial ecosystem that was working there all that time back. And if we could see something like that on another planet, particularly Mars, that would be fantastic.
Right. Oh my.
Well, we can almost. We can see mud rocks on Mars, and we can see very small, circular, spherical bits in them. We don't yet have the instruments in situ, and that's what I'm working on.
Wow.
So that we could eventually, maybe before we bring stuff back, but who knows?
Right. Wow. It's just truly, truly amazing. I know so much more about biosignatures now. Unfortunately, we're just about out of time, but I always like to ask of all of my guests, here we are at the cross section of kind of arts and sciences. Is there an artistic practice that you either like to do yourself and or appreciate? And of course, I know you've got lots of music in the family. And so just curious for yourself.
Yeah, I'm involved, I suppose, in two arts. One is the art of storytelling, which I'm still developing, particularly telling science stories to the general public. I'm a volunteer for the NASA Speakers Bureau. But my really greatest love is the culinary arts, which I do practice. I'm a member of a very small, distinctive club in Los Angeles area called The Dish. And every month, one of our members will host an evening, but before they do, they put up on our website the theme of the evening and many intricate recipes. And members rush to sign up to choose one that they will produce. And then we all get together on the evening, and people produce the goodies. It'll either be a starter or a dessert or a side dish or a main dish, or maybe a number of small main dishes, which people, if we have a tasting menu, and we sit there and we eat and we drink and we discuss the recipes and we have fun. And I've got to say, as in science and the culinary arts, I think if we're not having fun, it's not worth doing.
Absolutely. I could not agree more. And I'm hoping at some point to maybe get an invitation to one of those dinners.
Hey, play your cards right here and then you will.
Well, Max Coleman, thank you so much for helping us gain knowledge through the lens of creativity here on Artful Science.
Thank you, Aaron, for inviting me.